Good day, everyone. Thank you for coming for my talk. I'd like to speak about a project I have in Moscow State University, which my students and I work on simulation of global networks. I'm graduated from calculation math department of Moscow State University and remained in academia, where I'm now after PhD period, have a few students working on the project of simulating some aspects of network. And my background is mostly in security area. I worked with intrusion detection systems, Snort, for example. I did some antivirus research, optimizing algorithms, and implementing data mining algorithms for malware detection. And in simulation, I work on systems efficiency measurement, such as high load systems, for example, DDoS systems analyzing, and so forth. My agenda is as follows. I will start with some introductory part, what is the area from our point of view. Then I'll have a few words on simulation and modeling, so the audience will be intact with the flow of the presentation. And then I'll describe the model that we're implementing and components of it, and also show some examples of components running and outputs, and discuss some troubles we're running into, some problems that arise when we try to simulate large-scale networks. What's in the area what we are looking at? We are looking at the network which is a large-scale one, like regional network or the whole internet itself, for example, which is pretty large by numbers of hosts, of routers, of packets, and so forth. And network main duties are to maintain operation, such as updating router tables, for example, and providing service for network servers and their clients for exchanging traffic. And there we have some metrics to measure via simulation. Malware is spreading across the network, must be located somewhere, and using some algorithms, choosing targets and trying to attack them to spread further, after which it can perform attacks, misuse, for example, DDoS attacks, or sending out spam. And security systems are located on network hosts or subnets to prevent malware from spreading, to detect malware, and so forth. So we're looking into firewall, intrusion detection and prevention systems, and host antivirus types of security systems. So, said all this, what is the common ground for malware to look into in the whole network? From our standpoint of view, it's traffic generated both by malware that tries to perform attacks or trying to spread in the network. So all the actions that can be performed by malware are affecting traffic that is transmitted in the network, and consequences of the attacks also can be measured with traffics being transmitted or ceasing being transmitted, and infrastructure state. Also, sure, there is some measures that cannot be discussed in this space. For example, rootkit ability to defend themselves from antivirus systems on host, but it also can be implemented in the model, like malware ability to defend, to stay against security systems. So we are looking into traffic model as the measurable thing, and everything other could be implemented via stuff like decreasing security systems efficiency, for example. Okay, and the scope of our project is called Global Network Hybrid Simulation. I will just explain why we are going to make a hybrid simulation engine. And the scope is as follows. We have large-scale networks. We want to analyze security issues such as malware population and network performance, network security system performance. And another interesting question we run across is the problem that it's pretty much hard to not only fit some requirements, but also set requirements for such a complex simulation task. So we need to create simulation engine that is computationally feasible, both in terms of memory and CPU, and we need to think beforehand about simulation setup data availability. Speaking on modeling simulation, there are plenty of efforts in simulating of networks, in simulating of network protocols. Most of them are using packet as a basic entity, and packet sending and packet receiving events they are handling to advance simulation time. And if we look into model is an abstraction of object. So we need to describe an object in a way that is meaningful in terms of our question of simulation, and make some approximation, which is changing functions to more simple, or assumptions like removing some features that are not that important to reduce complexity of the model. And in complexity, two main aspects are object entities count, so how many objects do we have to keep in memory, and the number of events, which actually prevents us from adjusting model time via local time. There are plenty of approaches, and some of them are more complex, some of them less precise, more precise. For example, this one is describing, this picture describes packet exchange, while this one describes system dynamics and this basic epidemiological model, suspectable, infected, resistant. But a few words about going straightforward and using packets as a basic entity in simulation. Actually, it's good. If you look into engines that are used for simulation of, for example, protocols verification, they are pretty much straightforward. They are using a program that will be verified as a model, because it's already an abstraction of algorithm. And it can be used straightforward, and the results of simulation are exactly applicable to the subject. You don't need to do any assumptions, any analysis of our model output. But if you look into the subject we are running into, we will see the numbers that are pretty much removing the issue of using the packet as a basic entity. Because if we are looking on internet, for example, we have 100 million of hosts, 700, I guess, right now. well, let's say we take 100, and we can calculate approximately numbers of routers and packets per second numbers are pretty much removing the opportunity to use packets as a basic entity. Because the other problem is that in simulation you have to, you always need to think about entities of the model affecting each other. So you don't simply have 10 to the power of 10 events, but you have these events relating to each other. And the goal is to run actually faster than real time. So if you have packets per second 50,000, so you need to be able to parse at least this many events per second to be faster than real time, or else you'll be drawn back in simulation, so starting to get late just in time you've started the simulation, which restricts the model use from, for example, being introduced into real traffic system, or just simply it's not good when your simulation engines work slower than real time. So what can be done to reduce the complexity of the model? We can get rid of some of entities and events. We are running into some errors. We can measure this error level and set some borders which we are not going to cross. But this way we can significantly reduce the complexity and memory demands. And this can make actually feasible the whole simulation engine development. Well, our approach to describe network model is as follows. We want to split the network in more meaningful for us part and less meaningful. For example, we can choose a small segment of the network to be observed part of the network, and describe the channels to the outer segments, which can be pretty much the 80 to 90% actually of the host count, which will communicate traffic to us and affect our network. So we are not just simply putting them away from the model, but keeping them inside. And look into observed network on the autonomous systems level. Under which we have border routers infrastructure, and inside we have some domains which we are describing as vectors of characteristics. And this way we are reducing the large amount of entities in the network model. If we are speaking about traffic, we want to get rid of the packets at least for the vast amount of communication. How this can be done? We can concentrate not on packet sending events, but on sessions, for example, going one level up from IP to TCP. But if we are doing so, we are running into problems with error handling. So we need to find a way to find out not only how to lose packets correctly, delay packets correctly, but also how to make applications work correctly if they are losing some packets and we are not actually have the exact packet which we've lost, but we are getting the percentage of lost packets. How can this be done? We are using traffic flow approach, which was discussed in a few papers for some time. we are using traffic flow from one domain and autonomous system to another. And we still keep some packet level simulation because we need to be able to implement such stuff like routing updates, which will be critical for the whole network behavior. And technically, we have time-stepped flows calculation for every traffic type. So we have traffic types for malware, few of them. We have a few traffic types for legitimate usage of the network. And for routing, we are calculating weights that will regulate flows, and routing update tables are updating weights on the corresponding router in the graph of the network. So if we look into traffic lifecycle, traffic needs to be generated, traffic going to be transmitted, and traffic going to be consumed. On every stage, we need to dig into questions deeper to understand what are the problems are during the generation, transmission, or consumption. Because if you are running on packet level, it's pretty simple. You just get an automata or algorithm in any other form that is using some algorithm to choose address, for example, choose how fast it can run on some host, to find out limitations that it have to for amounts that it can generate in any given time. Same for transmission, same for consumption. If you are going to read off host level and going to read out of packet level, you need some means to understand how address will be generated and what is address in this representation of traffic, and what amount actually is being produced. Same for traffic transmission. We need to understand how to represent queuing handling algorithms such as RED, for example. We need to figure out delays, how to handle them. And if we are looking into the question of router state, we need to understand how traffic is affecting transmitters. For example, how packet size to packet count to traffic size count ratio affecting any given router we are using. So in our model, we have something like three-level architecture. We have a model for traffic generation, which is tied to violators model in case of malware, or user model in case of legitimate traffic. We need application level traffic model, which will shape the amount of communication between software on the network, the way it looks like on network protocols using the theory of self-similarity, which comes handy here. And on network, we need to use topology, and we need to use routing tables, routing information to calculate delays, to calculate traffic loss correctly. And we need to coordinate so traffic we lost here doesn't, so we don't receive on the end more than we sent sometime back. If we speak on some more topic that is closer to us here, about malware, we can speak about malware parameters that are often used in epidemical model, in simple model, multi-agent models, for example. that are describing malware dynamics in networks. We have population, which is counted somehow placed on the network. It has some spreading mechanisms, which involves attack vectors, choosing targets, and intensity it tries to spread itself. And we also can have some payload execution, for example, performing network scans, performing DOS attacks, and so forth. Coming to this question, we found out that it's important to split the whole idea of addressing at malware and maybe on some legitimate protocols to two groups. First group is single targeted type of communication where the agents spread across the network communicate to one server. For malware use, it will be corresponding to DDoS attack, where web server DDoS attack, for example, or web server usage, where we have one point and we need to calculate correctly delivery of the traffic from the different points of network to this point of the server is. And multi-targeted addressing is when malware is trying to spread itself. For example, it tries to try some algorithm like IP address generation, and this type of activity is should be calculated for every domain or every autonomous system, and can be described as the ratio of the traffic spreading across the nearby domains or whole domains in the network, because it can be done the way it was made with single targeted attack. And the following interesting question is, how do we handle switching of malware from one activity to another? If we take, for example, botnets, the botnet life can be divided in spreading part and performing some service for the bot master. So we need to describe the model of how malware is switching from one activity to another, or mix somehow both activities. And here also we have some interesting field, which is like an opening in our project, where we can install additional models of how switching occurs. For example, how fast the whole distributed network of agents can be switched given the state the network is, and given the place from which the command comes from. And here we need to implement, we are going probably to implement some algorithms of command and control channels. So, for example, it should look completely different if we take centralized algorithm or peer-to-peer algorithm for command and control. And it affects both the speed of how command will be delivered and how fast the attack, for example, will start. Also, it will be interesting to work on the violators model for this task, which commands how botmaster changes commands over the time, and how it affects, how fast it can affect the bot network, for example. But it's slightly into the future, where the rest of the components are ready and running. So I've touched the problem of malware, but looking into this question, we can have where we've came across some more advanced stuff that malware versus security networks can be analyzed, can be introduced into the model. such as using the noise level of malware generates to correlate with how fast it gets cured, how it can be, how affects the presence of the malware, the fact that it fortificates on host and is hard to get rid of, or also the problems of now popular try and dropping technique, when one malware downloads a bunch of other malware tools and infecting hosts much deeper than ever before. And also we can implement some security system tweaks as well, which will affect as well as cleaning malware and blocking spreading attempts, which is basic, but also blocking command and control traffic, which will bring some root bots to the network, which keeping attacks on the services that are no longer wish to be attacked by the bot masters, for example, which are, as I know, is happening from time to time. And another interesting question is updates, how malware updates itself, how security systems updates and patching networks, it protects the question of patching window, how the size of patching window point where the patch has been developed to point where it has been installed affects the epidemics, and if we can tie patching window time to patching window time of malware, that when bot masters figures out that his malware being cured, for example, and develops patch himself against this patch to keep his bots alive, how fast can be security systems plus network administration versus bot masters to actually get rid of bots. It's another interesting question which can be simulated on this level of abstraction. If we look into security systems, we can consider them actually as a network service which accept the whole traffic that passes by them on the input, have some state, can have memory, and have some hardware they run, or have some limitations due to hardware, need to perform in real time, and can block, mistakenly block some traffic, which can be done either constantly, for example, which is closer for signature-based algorithms and systems, and can be not so persistent, for example, for blacklisting techniques and statistical analysis techniques. But in general, we can look into security system model like this. We have collection buffer, which is limited by the hardware. We have analyzer engine. We can have state of the system if we're using stateful analysis, for example, keeping logs for the established network sessions until they are closed. And we have some filtering, which is filter some malware traffic as well as some legitimate traffic. If we describe the model like this, we can then introduce some errors or failures to the security systems, which can be either scheduled, like we want to see what will happen if some security system will be falling because of attack on them, and we can introduce some shapes. It falls, it's recurring fall, or it fails and need to be manually reboot it because of the attack. And also we can try to look into the question of how different systems that are working on the same traffic flow going well together. How are they performing together? Is it helping in any way, or is it just increasing delay? How many systems do we pass in during the traffic flow from one system to another? Here's some simulation example from some traffic example from security system failure. Here we have malware traffic entering domain, and after the intrusion prevention system fails, we are going down and malware traffic jumps up. It's kind of the behavior that our model can reproduce, and that's how it can be introduced to the whole model of the global network. If we speak about efficiency metrics, we have, for every component, we can have efficiency metric which we either can have fixed, like a given parameter of any given simulation, or we can try to estimate. For example, we have malware population dynamics, which we can try to calculate, or we can fix and say that we have an epidemics that goes like this pattern, for example, and then calculate traffic from this epidemic, and try to figure how it affects our network. We have efficiency metrics as well for security systems, and from network point of view, we have some metrics that allow us to understand how user can feel the presence of security network and malware, to calculate some cumulative efficiency metric. Here we have some example of the statistical data approximation using our model of epidemical spreading and as well as traffic generation. So we have this is a sample of code red, and we have the model that is model of traffic generation run on top of malware growth dynamics. So it's feasible to find a correlation and to tune this model for real samples back in history. If we speak about network that is affected by the activity of malware and security systems, we can look into packet loss, traffic delay, jitter, which is the calibration of delay, and also we can add to the mix and host malfunctioning and network infrastructure overload, which will be like a large-scale incident, which will reduce the overall possibility of network usage. That is the reason why we need to keep packet level. As I mentioned above, we are using BGP routing model for autonomous system routing updates. So we can have actually real-life dumps of BGP tables and try to run updates across our simulation network, calculate what update will come to, and try to announce updates, knowing the state of the channels in simulation. If we look into problems with network services, how is this simulation engine can be useful for them for preventing them to fail. This model can be used to understand the additional horsepower is needed for DDoS, for example, and how long will last, as well as the services themselves, as well as infrastructure such as DNS, for example, and how useful can be alternative services locations, how far, if we look into problems from the time the botmaster can switch malware from one point to another, and how fast can we switch, and how fast users will switch with DNS updates and so forth. And we can try to play with some congestions technique, switching to static versions of websites, for example. Try to look how it affects network, if it's a network overload attack type, or how it overloads the server itself. And patching window is really interesting to look into in epidemic staying alive and not giving up to antivirus updates or vulnerabilities patching. Here is some cool looking visualization, which you can patch part you can't skip. So we have a few resources. Here we have attack on them. This line is IP address space. We have some flows that are related to this resource in time. And the final question, but it's actually appeared to be a pretty complicated one, because we need to get through mathematical complexities, which is pretty well documented, I can say, and we can run through information security troubles which we're working on, and we know something that we can use and where to find information. But gathering information to run experiments is pretty hard. For example, recently we tried to find bandwidth from global network from internet. We've tried to build a graph that connects different parts of the network. We ran across few measurement reports which are not really repeating each other. They have some points different. For example, most of them just simply don't have Russia on them. It's not interesting for them. And for some reason, I am interested. So we have some troubles with collecting data. We are using such techniques as looking into registries, databases, RIPE and IRIN and so forth, looking into reports, and also we're going actually to write some own tools to scan network, to gather network. It's a question maybe if you have an ideas how it can be helped to find bandwidth, to find out inner structure of autonomous systems, inner connection structures. It can be useful right now. We have no troubles with malware statistics. We've made some homework on this, and we have some pretty much a base of malware statistics spreading. I'm not sure if I published it somewhere, but it's available. Here are some thoughts about how the whole system can be used. We can analyze impact of security system introduced into the network to understand is it a good thing from the impact versus price point. We can try to run some congestion algorithms which are not possible to test either on real network or packet level simulators or even some non-hybrid, fixed level of abstraction simulators. And we can look into network stability issues because we have a BGP module in the network simulation. We can try to look what happens if we have an attack, a DDoS attack, for example, and in the same time we have some malicious advertising of BGP route routing, for example, and so forth. And speaking of plans, we are pretty much finished, I guess, with components and finishing integration. Test runs will be held this winter. I hope to publish the project, make it public as well this following year. We are open to discuss and cooperation. We are not yet tied in any way with anybody in this project, so we are open. And I'm trying to bring some interested people to Moscow State University and some people from other conferences who are interested. If you are interested or you have somebody who is a student, a PhD student, who's interested in simulation, in malware simulation, you are welcome to contact me. So here are some references, keywords you can Google and find the large amount of information of the subjects that were touched in my speech. And that's it. My contacts are here, as well as Twitter, LinkedIn, or whatever you find. It's all here. I'll be glad to discuss it later as well as right now. I'm ready for questions. Thank you.
Do we have?
Actually, a bunch of questions. First of all, you moved from a packet level to a flow level simulation.
Yes.
Can you really manage to simulate the effects of the TCP congestion control? For me, it seems like very hard to get this feedback loop because TCP traffic kind of depends on the network conditions. So,
I see. TCP congestions and any loopback control is pretty different to get into the model. We can manually add effect of TCP congestion into the model. Like, for example, we are going to reduce a traffic window on the state of the following router. I possess the knowledge how surrounding routers are loaded. So I can calculate in advance of a time. I'm not really getting congestion control packets for me, but if I know that congestion protocols will kick in, I can just order myself to reduce the flow in some time advance.
Okay, thank you. And second question. This looks to me quite interesting to simulate the optimal distribution of anycast nodes for DNS deployments. Any ideas on that?
DNS
anycasting.
DNS anycasting.
To how to place name servers for optimal resilience against attacks.
it might be interesting. I haven't thought about it. Thank you very much. I'll speak to you later. Thank you.
Do we have another question?
Well, you might ask where lolcats are. No, no lolcats for us. Okay.
Okay. Well, excellent. Thank you very much.
Thank you.
Until 1.